Human beings are very curious, and their curiosity can be felt everywhere in all fields. One particular place it will never be vanquished, and that is the origin of everything in the universe. I'm Ahmad Mansoor Ramizy, and this is Astromaniac. Humans ask, where did we come from? And for many thousands of years it was just the deities and gods that filled the gap. But eventually humans began searching for answers through other means. But in order to do that, they first had to understand what they are and where did they come from. And that is where science comes in, and the many hundreds of scientists that dedicated their whole lifetimes in order to solve these kind of questions. And one of those scientists in particular was Charles Robert Darwin, with his revolutionary idea of evolution through natural selection. Okay, Darwin solved the question of life and how we came into being as a species and as an animal and as a mammal. But how about the planet? How about the solar system? And how about the stars and everything else there is in this universe? It wasn't until many decades later that we eventually started to build up our ideas and theories about the creation of the planet, about the stars and everything. And then we were left with another big question. How did the universe come into being? What happened during the creation of the universe? And did it have a beginning at all? In the past centuries, our insight to these kind of questions were extremely limited, until Edwin Hubble, a young astronomer in the US. Now, Edwin Hubble, unlike the misconception at his time, proved that the universe isn't just the Milky Way. And he proved that there are many more millions of galaxies outside our own galaxy. And in fact, that these galaxies are actually residing and they're expanding. Astronomers figured out that the speed that they were going away from us was actually sometimes faster than the speed of light. So how is it possible, according to special relativity that Einstein proposed a few years earlier, that we are able to see and witness these galaxies that are residing from us at higher and higher speeds proportional to the distance from us, even sometimes faster than the speed of light, and still not breaking the laws of physics. Now, what we found out was very interesting. It was that these galaxies are not moving themselves. It's the space between these galaxies that are actually stretching and moving. Now, this was a groundbreaking discovery. What happened next was that astronomers and scientists came together, specifically Georges Lemaire, who proposed that, okay, so if the universe is expanding now, if we run the clock backwards, we eventually find that the universe gets compressed and gets denser and hotter, and then eventually you're just in the single point of creation, which we now call the Big Bang. Now, the Big Bang is where the whole universe started off. It's everything and anything that we can witness today came from this single point that expanded into this universe we see today. Is there anything else to the Big Bang? Are we certain that it happened? And what other models and theories do we have about the creation of the universe and about the first moments of the universe? Now, to answer these questions and many other amazing questions about the creation of the universe and the Big Bang, I asked my friend Rafi Hessami from Stanford University to join us here today. And hopefully by the end of this video, we'll be able to leave with a clearer picture of what happened during the Big Bang, as far as we know, and eventually did the Big Bang actually happen or not. So please stay tuned, guys. Mr. Hessami, hello and welcome to Astromaniac. I hope you're in good health.
Yeah, thank you very much. I'm happy to be here. Yeah, doing well in Florida. Hope everyone's well over there too.
Thank you very much. Well, it's the usual coronavirus situation here as well, so I hope you're staying safe and staying home.
Oh yeah.
Let's get to know you a bit more. Okay, personally, we have some contacts. I know you, but let's have something for the audience about what you're doing now and how did you become interested into physics. And I also think you're interested in astronomy a little bit as well. So where were you born and what are you studying now?
Sure, yeah. I was actually born in Maryland, in the rural countryside of Maryland. And I grew up in Florida, also kind of a rural, small town, nice place. So during my childhood was kind of where I developed a lot of my interest in science and physics. I'm not so sure why. I think I just always sort of gravitated to it. I think I liked kind of the idea of being able to like objectively know things, because there's a lot of things in the world that you really can't objectively know. With things like politics or society or whatever, it's fun to learn about, and I like learning about that. But I tend to kind of have an issue where I can't really ever say like this is absolutely right. I always have a little bit of doubt, because you can't really do an experiment and prove stuff
Mhm.
for the most part. So I
Mhm.
always like the objectivity of science. And for physics in particular, I like that, of course. And I also liked how it tended to be very, very fundamental. It's a lot of just these kind of short, really succinct rules that you can write on like one page of paper, and you could spend your whole life studying it and analyzing it and seeing how
Mhm.
all that stuff works out. I mean, I took a year-long class that's basically the result of like one equation that you can write on one line. That's basically how quantum,
Wow.
yeah, it's basically how quantum mechanics in college works. So yeah, anyways, that's how I just developed my interest. In high school, I did a lot of the science fair, and I had a really good biology teacher actually, who was a really big inspiration and really helped me along with that. And I think that's where I kind of developed the confidence that I could be a real physicist, because for the most part, it's not really like a real job for most people. It's kind of something you most people don't really imagine that they can be. So
Mhm.
yeah, then I went off to college at UCLA where I studied physics and I minored in mathematics. And I worked in an accelerator physics lab where I built like particle accelerators and designed all kinds of experiments like that. And there I developed sort of a little bit of expertise in that area. And then over time, I had an internship during college at SLAC, which is a giant particle accelerator at Stanford. There's a couple particles they actually discovered in like, I think the 70s there. And then this past summer, I worked at CERN in Geneva, which is kind of like the big spot for particle accelerator physicists and really a lot of the high energy physicists these days. That's where the Higgs boson was famously discovered a couple years ago. We had all our lecturers in that room, which was really nice. Yeah, and then I got into Stanford University for a degree in applied physics, where I'll be starting in the fall. Very excited to work there. Very excited to go back to where I worked 2 years ago, since Slack and Stanford are basically the same. And yeah, that's pretty much it.
Thank you very much. We have something else in common, I believe, and we share the same ethnicity. And can you shed a little bit light on that, please?
Yeah, absolutely. My dad is actually from Afghanistan. He was born and raised in Kabul in Sharanao. He's from the Hessami family. If anyone happens to know any of us out there. And he left in 1979. First, he went to Germany to study medicine, and then he came to the U.S., where he is now.
Thank you very much about that, and not to mention that we are very proud of what you're doing and all you have done until now, and what you're planning to do in the future as well. What can you tell us about the origin of the universe, and what different models and how many different theories do we have to explain how the universe began?
Absolutely, yeah. So our big, pretty much top cosmological theory is the very, very famous Big Bang theory that everyone kind of likes to talk about. And that's a good name. A name that was actually originally applied to it kind of derisively. It was this guy started calling it that to make fun of it because it sounds kind of silly, I guess. Yeah. So basically, the main principle behind it is that we imagine the whole universe is starting at an infinitely small point, literally just a single point in space, where all energy and mass and really everything that we consider anything is concentrated. And because of that really, really high energy density, you get a very, very rapid expansion. It's kind of a nuanced thing from general relativity, but when you have these high energy densities in a region, the space there expands. And that's how we get a lot of spatial expansion. So yeah, basically we start at this giant single point that just immediately explodes incredibly rapidly. And so very early on in the universe's history, we don't really have any matter forming. For matter to form, you need things to be kind of cool. You can think about that sort of in terms of the amount of structure something has. So like a solid has a lot of structure and it has to be kind of cold. Liquid, there's less structure, it can be warmer, and then a gas or a plasma even less, and it's hotter. So at this really, really extreme limit that basically was the hottest the universe ever was, there was no structure at all. There weren't even really protons. They were just kind of coming in and popping out of existence. So as it expanded, the amount of energy per region went lower and lower, and it cooled off. So eventually, you have what's called baryon formation. Baryons are the kinds of particles like protons. Protons are really the only one that we regularly interact with. So we start seeing protons forming, and then further on in the universe's history, as things get even cooler, we see those protons able to capture electrons. The electrons are no longer so hot that if you have a proton, they just whiz by. They're slow enough that they can get attracted and start orbiting around it and all that good stuff. So that's basically the origin of matter. And it's really amazing how far back in the universe we can look with really incredible accuracy. It's only relevant to like the exact moment of creation that things are kind of unclear at this point. So we have to give ourselves a pat on the back for really how well our theories have done so far.
That's amazing. And so something else just came up in my mind. So if you're saying that during the Big Bang and during the event we call the Big Bang, during this expansion, this rapid expansion, we believe that something happened around 10 to minus 33 to 36 seconds after T0, after the moment of creation. Something happened, and it resulted on a chain of events that led to the creation and the formation of galaxies and stars and clusters and eventually us humans. So what was this, and why is it important?
Really early period where the rapid expansion is even more rapid than we expected. We thought it would be really fast. It's like many orders of magnitude even faster than that. So it didn't really fit the model, so it was kind of an open question for a long time. So one of the leading theories at the moment is it's just sort of called inflation theory. It's a very straightforward descriptive name.
Mm-hmm.
So basically it imagines, well, there are a couple of variations, but the main variation is that there were these particles, usually called inflatons, that haven't been proven to exist yet, but are, maybe they exist. We don't really know. You can't really say anything about it. But they basically cause the universe to expand even more rapidly. And during that period, the energy distribution was pretty uneven because it was just so fast, it couldn't settle. So any tiny, like absurdly small deviation from exactly even just got amplified. So as a result, the energy spread throughout the universe became very uneven and blotchy. So one region would be very hot, one region would be very cold. And basically that's how things turned out.
That's quite amazing. It's mind blowing. In fact, I'm already quite fascinated with where we're going with this. So coming up with this, we know that something happened because of the footprints left by the Big Bang. And what can we say about these footprints? What are they? And specifically talking, what are the evidence we have right now that such an event actually happened, and when did this happen?
Yeah, that actually uneven distribution of energy is probably the strongest indicator. It's called the cosmic microwave background radiation, and it's pretty incredible. Just by using a good telescope that has some infrared capabilities and stuff like that, but nothing really like too fancy, not something unachievable by most, large organizations. We can look basically back in time and see the light coming to us that was created right when the universe was first born. It's lived that entire time it was created at that moment, and it's just been traveling around until it hits your telescope. You can basically look at the earliest moment in the universe's history from that. So from that, we can measure and look all around, and we can see the cosmic microwave background radiation. And the structure of that is very indicative that it kind of came all from a point, from the famous Big Bang. And that's probably the strongest evidence we have for it.
So, in a sense, if we have stronger telescopes and stronger equipment to look the further back, as far as back as we could, we'd be able to have a clearer picture of the universe during its infancy. And one of the leading telescopes, I think that's about to launch like in just a few years. It's been quite delayed for a very long time now, is the James Webb Space Telescope.
Yeah.
And I believe it's going to be monumental moment for us all if we were able to look back, just right at the moment where light was able to escape. And speaking of that moment, why was light trapped during that time we call the Dark Ages? Why was light trapped, and why couldn't we see anything during that time?
Yeah, basically it comes back to the energy levels of the universe. It was just so hot that it was hardly meaningful. These sort of photons were just everything was being bathed in photons. It was so energetic, they were all over the place, so you couldn't really get any kind of clear picture. Like you said, yeah, you wouldn't if you were there, you would be pretty much instantly incinerated. But if you were there and somehow able to look around, you wouldn't be able to see anything. It would be just all kinds of light just bombarding you at all times. So it wouldn't really even be like a meaningful picture or anything like that.
And then we have the Planck error, which is just a very very tiny amount of time where everything is kind of mixed up and everything is just in this jar in this mixer. And how are we able to study this? Like, there is literally no way we can study that as it is. So what are the substitutes, if we can say, for studying this Planck error? And why is it important if you want to study it?
Three main ways we can look this far back in history. One, giant detectors that we set up and we just wait for cosmic particles to come and hit it. So what's really key about that period that makes it different from anywhere else in the universe's history is how hot and how energy dense it was. Really, the history of the universe is, for the most part, just a history of things cooling down and the change in structure you get from that. So there's a lot of thermodynamics. It's kind of incredible how all these things connect together. So anyways, you have these detectors that are giant arrays of sensors, and you just wait for particles from deep in space to come and impact those. So the advantage of that is that you can get these crazy high energy particles, things far, far, far more energetic than we could ever produce on Earth, to hit the detector. And from that, you can learn a little bit about what it was like when the whole universe was that hot. The problem with that is that you're basically just relying on luck. You're just hoping some particle is going to come in and strike it. The second way, like we talked about a little earlier, is those giant telescopes. Those you can look further and further back in the history, in the past of the universe, and basically see that general image. Again, you kind of have the issue that it's not very controllable, and since it's a telescope, you can really only use light very much. You can't use like muons or other things that might be very old for those purposes. The third way, and my personal favorite way, is using particle accelerators, like the big one at CERN, the very famous LHC. What happens there is that you collide two proton beams, and at the collision point, they're such high energy, it basically mimics those early points in time. Stephen Hawking, before he passed away, actually said that particle accelerators are the closest thing we have to time machines. In one sense, he meant
Wow.
because of the effects of special relativity, but in another sense, because they get just so hot, it's basically like we're creating a tiny, tiny sample of the early universe in there. And we can study that and see basically how it explodes and learn all about the structure and everything that's going on inside there.
Wow, again, it's just fascinating, and I hope the viewers are paying a little bit attention to the details that's involved here. And like, we come up from something so far away, so back in time, and then we're coming, like, it's like, how long has it been? Like 13.8 or 13.7 billion years ago since the Big Bang, and then we come all the way 13.7 billion years after the Big Bang, and on a very tiny planet somewhere around the corner of a small galaxy, like relatively normal galaxy, and we have these creatures, these human beings, and they're trying to create and mimic what happened all those years ago, and mimic that over on the surface of the planet, just with metals and electricity. That's just fascinating. I'm really into like accelerator physics, and CERN has been like one of the most important and most fascinating places for me ever since I got interested in these stuff. So now that we what is the future for particle accelerators? We already know that CERN is very famous, and already I think you were there last year, and I believe it's been dismantled. They're trying to, I don't know, fix some stuff, I think, and so it's non-operational, and it's going to be operational in a few years. But um, what can we do with CERN? Like, we had the biggest achievement of CERN in 2012 when the Higgs boson was detected. But what else can we expect from CERN? And will CERN be obsolete in a few years? Should we look over for Wakefield particle accelerators in the future?
Yeah, that's really the multi-million dollar question in this case. So there's a couple possible ways we could go with it. One, we already have the LHC. What they're doing right now is called the LHC High-Brightness Upgrade. So basically, they'll change some of the structures and some of the machines in there, and they'll be able to get a lot more of these particle events and basically get a lot more data out of it. Something like, I think, thousands, maybe even millions times more data. So that'll be really promising.
Wow.
Uh, so what we have right now is kind of an interesting situation. It's kind of both the best of times and worst of times. We have this really fantastic model, the standard model, that predicts virtually everything you could really want.
Mm-hmm.
We've done a really good job with it. Not to pat ourselves on the back too much, but it is really, really good. Uh, so, but
Except
it has
gravity, of course.
except gravity. That's the one big one. Uh, yeah, gravity, and it has a lot of kind of weird aspects to it. I think it's 27 undefined parameter or defined parameters that don't really come from anywhere. Things that are just constants that are just kind of there, and that's kind of
Hmm.
weird. We don't really like our universe being the way it is just because a number just is. We like to have some kind of meaning and some kind of reason. It's almost an aesthetic criteria. It's kind of artistic in a little bit of a way, but that tends to make people question it a little bit. Anyways, in terms of what can actually be done, right now we have the Higgs boson discovered, and we know it exists, but we really actually don't know all that much about it. So, one of the big important things
Hmm.
that would be next would be detailed studies of the Higgs boson. There's a lot of interesting directions it could go. One, it's possible that the Higgs isn't really one particle and that it's a whole Higgs subsection of the standard model. There may be up to like 5 different kinds of Higgs particles. And with the LHC right
Hmm.
now, we wouldn't really know that. So one of the proposals is building something like the LHC, but even bigger. It would be 100 kilometers in circumference. And if you've ever seen a map, maybe we can throw up a map graphic or something of the LHC. It's like this, and it stays pretty much mostly in Switzerland and France. But the bigger upgraded version would go all the way around a large chunk of France and into Italy, and it would actually
Oh,
go under Lake Geneva. Yeah, before coming back into CERN in Meyrin, this
wow.
kind of small, pretty Swiss town. Yeah, so that's one option. There's another option that CERN's considering that would be a big linear accelerator. So traditionally, a lot of the
Hmm.
discoveries, the big kind of brand name discoveries that you see like on the top of magazines and stuff like that, are made by proton particle accelerators because they're able to get to higher energies. But the really detailed, the fine structure of things are usually done by electron accelerators. And let me tell you why.
Hmm.
With protons, you have 3 particles in each. Every proton is made of three particles, up and down quarks. And when you slam them together for an event, it's kind of like throwing 2 bags together. 2 bags with like 3 bowling balls or something like that. You throw them together, and
Oh.
then everything gets thrown everywhere, but you don't really know that initial state. So it's hard to do a lot of reconstruction. So they're pretty big error bars, and you can't really tell stuff that well. With electrons, they're true point particles. So they come, hit each other,
Hmm.
and you know the exact initial state. So you can get much, much more precise. Yeah, CERN is considering building that. One of those 2 options will probably be made. Which one now? It's kind of up to the physicists and the scientists, and also a lot of government people. These things are expensive, so there's a lot of politics involved. The
Hmm.
other, yeah, there are 2 other main options that are also in the works. There's the ILC, which is my personal favorite, in Japan. That would be a similar linear accelerator, what they call a Higgs factory, because it makes the Higgs bosons at such a high rate. And I'll talk about that a little more in a moment, because that ties into some of my work. And there's also in China the Circular Electron Positron Collider, which is quite similar. It's another electron positron collider, but they would build it there, and mostly, for the most part, China probably has the resources that they need for that. So yeah, there's a lot of these competing aspects, and there's kind of a little bit of politics to it, because there's a bit of prestige and, finding something fundamental about our universe. So all these countries kind of want to do it, but it's really expensive. So
thank you very much, Rafi John. It's a great pleasure, and thank you very much for all these beautiful insights about particle physics and accelerators, and then the future of accelerators in general. So just a quick question: is larger better?
Yeah, pretty much. In short, that's the key. But there is one exception. We have some new technologies that may be able to shrink everything we know about particle accelerators down orders of magnitude. Something that might be 100 kilometers today might be a single kilometer or even shorter in the future, thanks to plasma wake field accelerators, which is my specialty. It's what I've been working on for quite a while now. And yeah, I think that's going to be the future. What is essentially now that's huge will be tiny in the future, So in short, for now, large is the key, but in the future, small's pretty promising.
That's great, and I hope to see you one day directing a Wakefield accelerator somewhere around the world, in Geneva maybe, or somewhere in the US.
That's the dream.
That's a dream. So thank you very much again for being here. It was a great honor and pleasure. And as you're running out of time, maybe we can share a message to our audience, the Afghan people, and these young generation of people who are beginning to find interest in STEM and physics and astronomy.
Yeah, absolutely. Especially to young people who might be interested in science right now, especially the Afghan youth who might be interested in science. I think my message is that there's so much good you can do for the world while also following a passion for science, that it's really a win-win, for yourself, for your country, and for the whole world. There's a lot of achievements and a lot of improvements to be made. So yeah, I think anyone who has an interest or a passion for STEM, especially physics, I think you should really go ahead and really just charge ahead and follow that passion, because you don't really know where it'll take you from the start, which can be a little scary. But usually if you work hard and just go for it, it'll really work out well.
That's amazing. Thank you very much. Thank you very much, everybody. This is Astromaniac, and joining us today was Rafi Hessami from Stanford University in the United States of America. Thank you very much again.
Thanks for having me.